Okay, thank you for the introduction, Dr. Slavin. Yeah, so this is actually my first time joining the face-to-face conference without a facial mask after pandemic. And after a long time, it's I'm a bit nervous. I'm standing up in front of many many of you. Okay, so this is my this is Takahiro Moriyama from Kyoto University. Today, I'd like to talk about the spin dynamics and the transport in antiferromagnets. Okay, so I have two items today. First one is about antiferromagnetic dynamics and the resonance, where we control the antiferromagnetic resonance frequency and the line width, and also we investigate the spin pumping in antiferromagnetic material. The second one is the spin current it's about the spin current transmission in antiferromagnets, where we tested a high-speed transmission at a terahertz time scale. Okay, before I go into the detail, I'd like to acknowledge all our collaborators, different universities worldwide, and also the funding sources. Okay, so the antiferromagnetic spintronics is one of the interesting branches of the spintronics. And comparing to the ferromagnets conventionally used in the spintronics, antiferromagnet has a very small susceptibility and no stray field, which might enable us to make a high-dense magnetic memories. And the more interesting feature is the terahertz dynamics. Comparing to the ferromagnetic resonance frequency, we have like a few orders of magnitude larger frequency in the antiferromagnets. So one of my dreams is by injecting spin current, when we excite the spin dynamics, we can have like a terahertz emitter using antiferromagnet. The most important thing is that I think the antiferromagnet is a material that can harness the terahertz technology and spintronics. Okay, here the antiferromagnetic resonance. I'd like to explain the antiferromagnetic resonance. So the antiferromagnetic resonance is basically distinct from the ferromagnetic resonance. So the left image shows a spin precession in the ferromagnet, where we can describe by this equation of motion. As you can see, the ferromagnetic spin precession can be precessed in the same phase as the ground state. But on the other hand, antiferromagnetic dynamics is different. By satisfying this equation of motions, we cannot really have the same phase. I mean, it cannot really maintain the anti-parallel configuration while we have a spin precession. And of course, this is why we have the exchange field in the antiferromagnetic resonance frequency. So if we plug in the typical field for the say exchange field, and also the effective field is corresponding to an isotropy field, the typical frequency can be up to 1 terahertz. Okay, so we need to do the measurement in the terahertz range in order to characterize antiferromagnetic dynamics. So the setup we use is basically the CW terahertz spectroscopy, where we have the terahertz emitter and the detector pair, and we have we just put the sample that we want to characterize in between. We can scan from 50 gigahertz to 2 terahertz, and we can also change the temperature, and the terahertz power is about 1 microwatt at 1 terahertz. So this is a typical, so we can basically do the transmission absorption measurement by using this setup. So the typical transmission data for the antiferromagnet is a typical nickel oxide bulk material. We can see a very sharp peak right at 1 terahertz. from that, we can actually characterize a damping constant by fitting with a Lorentzian. And another important thing is that by plotting this resonance frequency as a function of temperature, from this temperature dependence, we can actually characterize the intrinsic frequency omega 0 at the frequency at 0K, and also the new temperature of the material. So from here, I'd like to discuss how we control the antiferromagnetic resonance frequency as well as the line width of the resonance. So as you know that the antiferromagnet doesn't really respond to the external field. So unlike the ferromagnetic case, even if you apply the external field, you cannot really change the resonance frequency that much. So by looking at this equation, actually what we can do is either we change this exchange field or the anisotropy field of the material. So in order to do that, I think the easiest thing is we say just dope the nickel oxide, for example, with a different cation. So here we dope the nickel oxide with, say, manganese doping. It's a magnetic doping, and also lithium and magnesium. So lithium actually have an effect that narrows the band gap of the nickel oxide, and Mg has basically is enlarging the band gap of nickel oxide. Okay, so this is a summary of the say intrinsic frequency and also the new temperature as a function of a composition of different doping materials. And basically, you can see that regardless of the doping materials, as we dope the material, we basically decrease the near temperature as well as the intrinsic frequency. But we can see a different trend for different doping materials. So here, we basically assume that the near temperature is kind of proportional to the exchange field. Therefore, we have this kind of a quadratic relation between the omega 0 and the near vector, so near temperature. We just compare the omega 0 and the near temperature for different doping experiment. We can conclude that this manganese doping basically have the effect that decrease the anisotropy field, and the magnesium basically decrease the exchange field. Okay, here we also characterize a line width or the Q factor for the different doping. So the non-magnetic material basically doesn't really change the line width. On the other hand, the magnetic doping, which is a manganese doping, seems to increase line width and also decrease the Q factor. So we kind of speculate that this magnetic doping basically increasing the magnetic inhomogeneity. Therefore, we have the larger damping line width, similar to the ferromagnetic case. So we also investigate different kind of antiferromagnetic material. This is alpha hematite, which is a material that has a very strong temperature dependence, which is associated with a so-called Morin temperature due to the strong temperature dependence of the magnetic anisotropy. So here we dope this material with, say, rhodium, aluminum, ruthenium, and I think the other one, indium as well. So the graph is a bit busy, but by doping, we can really change the antiferromagnetic resonance frequency. So if we plot the antiferromagnetic resonance frequency at the room temperature, we can actually cover the wide range of the frequency from, say, millimeter wave and a terahertz wave by just doping with these different materials. Okay, maybe this is good for application. Okay, so let's change the topic a little bit. So another effect which influences the magnetic resonance is, the famous is a spin pumping effect. So as you know, the spin pumping effect is an effect that the precessing spin can pump the spin current into the adjacent material. So this effect is widely investigated in the ferromagnet, but not much for the antiferromagnets. So we'd like to investigate this spin pumping effect in the antiferromagnet. So what we do was, we made like this nickel oxide platinum, either platinum or palladium granular granular sample, and then did a terahertz transmission absorption spectroscopy. So the schematics of the spin pumping effect in this system is kind of that. So when we excite nickel oxide antiferromagnetic resonance, this will pump the spin current into the platinum or palladium granule right here. So depending on the spin dissipation in this palladium or platinum, we should see the damping enhancement of the nickel oxide following this equation, where G up down is so-called the mixing conductance that characterize the spin pumping effect. And the S over V is where S is a nickel oxide heavy metal interface area, and the V is the volume of the nickel oxide. Okay, so this is a typical line width as a function of the composition of the platinum granule. So as you can see, as we increase the composition of the platinum, we see the increase of the line width. And when we plot, this is consistent because as we increase the platinum composition, we increase the surface area S. Therefore, we increase the damping. So when we plot the line width as a function of this composition, so to make sure this is due to the platinum or palladium spin pumping effect, we just have the control sample with the air pore instead of platinum palladium. So as you can see, this is comparing this control sample as we put the platinum and palladium more, we have a more line width enhancement. So from this data, we actually can characterize a G up down, the mixing conductance. So what we got is 12 per nanometer square for platinum and 5 for palladium. So this is really actually comparable. This strength of this spin mixing conductance is comparable to the generally assumed mixing conductance for the ferromagnetic case, like a permalloy platinum interface. Okay, so let's move on to the second topic, where I'd like to talk about this spin current transmission at very high speed. Okay, so as you know, the spin current can be carried by different medium. So in the conduction, in the metallic material, the electron can carry the spin. It's a spin current. And also the insulating material, or maybe conduction material too, a spin wave or magnetic correlation can also carry the spin angular momentum or spin current. So in the context of the antiferromagnetic spintronics, the spin current transmission through the antiferromagnetic material is one of the very interesting topics, I think. So there have been various investigations, including our own work. So here, we particularly want to investigate how first the spin transmission can happen in the antiferromagnetic material. So in order to investigate, we basically investigate the transient spin current transmission in the framework of so-called terahertz emission experiment. So here, it explains the terahertz emission experiment. So we have a 3 tri-layer made of ferromagnet and the antiferromagnet, and the heavy metal, which is basically platinum. Then we just shoot with a femtosecond laser pulse, and it will create, it will excite an electron which is polarized due to this ferromagnet. And this will flow the spin current through the antiferromagnetic material. If it reaches to this interface, it will, due to the inverse spin Hall effect, the spin current will convert to the E field. And this transient E field will emit a terahertz wave emission. This is a well-established experiment without this antiferromagnet. So this is actually, we collaborate with Professor Kimel and also Professor Mizukami in Tohoku University. Okay, so the sample we use here is actually a cobalt oxide different. It's another typical antiferromagnetic material. So we had this tri-layer of FCB and iron cobalt oxide and platinum, and with different thickness of cobalt oxide. So before doing measurement, we actually characterize the breaking temperature of this film with this sample. The breaking temperature is about like from 200 to 300 K, depending on the thickness of the cobalt oxide. So again, the measurement is done by this time domain terahertz measurement. So we just shoot with the terahertz, the femtosecond laser. And this measurement is actually capable of detecting the rotation of the terahertz wave polarization. So at the end, we can basically analyze how the this E field is rotated. So this is our actual result of the experiment. So here we plot the terahertz emission intensity as a function of cobalt oxide, from which we can see that up to 5 nanometer of cobalt oxide, we see this terahertz emission intensity. That means actually the spin current generated in the ferromagnet layer actually going through the cobalt oxide and reach to the platinum that emit the terahertz. Okay. The more interesting thing is if we plot the rotation of the terahertz polarization as a function of temperature, we have like a finite rotation of the terahertz polarization. And they actually vanish in the particular temperature, which is actually corresponding to the breaking temperature we characterize in this sample. So what happened here is basically considering this terahertz E field is proportional to the cross product of spin current direction and the spin current polarization. This rotation actually comes from the twisting of the near vector, which I just depicted in this image right here. Okay, so what we can say from this experiment is basically we can say that the sub-picosecond interaction of the spin current with the near vector can happen in this sample. Okay, here comes a summary. So first I talked about antiferromagnetic dynamics under resonance, and by doping the nickel oxide, we can control the antiferromagnetic resonance frequency as well as the line width, and also the spin pumping effect in the antiferromagnetic nickel oxide. And the second one, we characterize spin current transmission in time domain, and we prove that there is a picosecond time scale interaction between the spin current and the antiferromagnetic material. Thank you for your attention.